All right, here's our lesson on continuity. Big concept in calculus, knowing if a function is continuous. So a graph is said to be continuous if there are no breaks or holes in the graph. And by a break, it could be a jump or it could be an asymptote. If there are breaks or holes in the graph, it is considered to be discontinuous. And we call those discontinuities. So here, what are the types of discontinuities? So one is here where you have an asymptote. One is here where you have a jump. This would be like a piecewise function. And here's one where you have a hole in the graph. Different types of discontinuities. So examples here. Determine if the function shown on the graph is continuous or not, and identify the top if it's not. So look at number one. Is it continuous? And one of the informal ways to know if it's continuous is if you can trace the whole graph without lifting up your pencil. So number one, clearly there's a discontinuity. Where is the discontinuity? At what x value? Count to the left. So at x equals -5, what do we have? We have a jump. Can you follow it all the way through? This one is continuous. Here, is this continuous or is there some break in the graph as you do it? Clearly you can tell it. So at what x value? I see it's at x equals 1. And you can tell the type of discontinuity. We can call it a vertical asymptote, which is fine. It's a break. Is this continuous? Yep. Is this continuous? Well, there's something there. So at what x value? Go across to the left. So it's at -3. What is that type of discontinuity? It's a hole. Here, we have actually two of them. We have one at a discontinuity. And I know it looks like it's a little darker here, but that is an asymptote. So at x equals 2, we have an asymptote. And then at where the hole is, at x equals 4, that's obviously a hole. So in this case, there's two x values where something is not continuous. Let me just get some space here. Turn the page. Another big concept, calculus, is understanding the end behavior. What's happening on the right ends and left end? So we're going to rewrite this using similar notation with arrows, but we're not going to use right end and left end. So we have to understand mathematically what right end means and what left end means. So when we're talking about the right end of the graph, this is how we're going to describe it. And we're going to write it as, when we say as x approaches infinity. And here, because it can never get there, so you don't ever say when x is infinity. It's as it approaches infinity. So this is one way to write down the right end, and this is a way to write down the left end. So as x approaches infinity, where's the function? So the right end, where is it going? And you can see f at x is approaching negative infinity. As x approaches negative infinity, which is the left end, where's the function going? You can see the function goes to positive infinity. So can you write down these end behavior statements with arrows properly? So let's see. So how are we going to write the right end again? So we'll just remind ourselves it's right end. And to write the right end, we say as x approaches infinity, we write down f at x approaches, and that arrow says approaches, and you can see here also infinity. As x, this is left end, as x approaches negative infinity, that's left, you can see that the function is approaching also infinity. So we can see that both ends are going up. Here, again, so I'm not going to write it every time. So as x approaches infinity, what's the function approaching? And so you can see the right end is going down. As x approaches negative infinity, what's the function approaching? And you can see the left end is also going to negative infinity. end behavior. So the right end and the left end, not worried about the middle. So again, how do we write down the right end? As x approaches infinity, what's the function approaching? So if I look here, the right end's going to infinity. As x approaches negative infinity, what's the function approaching? That's the left end. It goes down to negative infinity. All right, graphs approaching a certain value. So as x moves towards positive infinity and negative infinity, it is possible for the function to approach an actual number, a finite number. So describe it. That's when we have a horizontal asymptote. So here, if you describe the right and the left end behavior, it's not going up or down. It actually goes to a number. So if you look here, you can clearly tell the right end and the left end are both approaching the same number, and that number is -1. So when we have a horizontal asymptote, that's when we approach an actual number rather than infinity or negative infinity. So describe the end behavior here. So again, as x approaches infinity, what does f at x approach? So you can see it approaches 0. As x approaches negative infinity, what number is it getting closer to? And again, the left and the right end both are getting close to 0. So again, the right end and the left end, you can see the horizontal there. Just count down to know what that number is. So as x approaches infinity, what's the function approaching? So that number is -3. As x approaches negative infinity, what's the function approaching? The same number, right? -3 on the left and the right side. Number 12, again, you can see that it's a number, right? A horizontal asymptote that's invisible there. And what number that would be? And look carefully, it's 2. So as x approaches infinity, the function is approaching +2. As x approaches negative infinity, the function is approaching also +2 on both sides. Look here, right end and left end, and then count how many down that is. It looks like -2. So you look at that line that goes across that it's approaching. So as x approaches infinity, where's the function approaching? And it's -2. As x approaches negative infinity, what's the function approaching? -2 on both sides. Here again, right and left end behavior, it's 0. And if I look here, the right end and the left end. So this right end, that's when f at x approaches infinity, the function's approaching a number. And that number, if I count down, is -5. The left end behavior, which is when it approaches negative, oh, why am I doing f at x? Just x. So as x approaches negative infinity, then what is f at x? This is left. Where's the left end going? And you can see the left end is going to positive infinity, not negative. All right, turn the page. Here's some more practice in terms of continuity and end behavior. I'm just going to put it on the same video. So, can you determine where it's not continuous? So you can see at x equals -2, it's not continuous. Why? Because there's a hole. How about here? It's continuous. How about here? Nope. What is there? At x equals 1, we have a vertical asymptote. We're going to soon learn in calculus to call some removable or non-removable, to know if there's a hole in the function that's considered removable, and that has to do with the limit at that x value. Here it is non-removable. That's going to be an important concept. But right now we're just learning about the concept of continuity. Then we're going to connect it to limits in calculus. All right, is this continuous? Nope. At what x value? So at x equals -3, there's a jump. Here we can see there's a vertical asymptote. At what number is it? As you look down, it looks like it's at 2. At number 6, oh, it's continuous all the way through. I don't have to lift up my pen. Here you can see at what x value is it not continuous. So at x equals 2 again. And again, you can see it's a jump. The next one, again, there's 2 of them, so I'm going to write both of them. So one is at x equals -2. It's removable, we say, but it's a hole. At x equals here, there's a vertical asymptote. So 1, 2, 3, over. we have a vertical asymptote. So those are all the parts of the graph that are not continuous. Here we have two vertical asymptotes. So at x equals -4, we have a vertical asymptote. At x equals +4, we also have a vertical asymptote on both sides. All right, turn the page. It'd be good to be able to name these functions too, right? So this is an absolute value function. Describe the end behavior. So we're going to say as x approaches infinity, then what happens to the function? So where's the right end going? Going to -infinity. As x approaches -infinity, that's the left end. What's happening to the function? It's also going to -infinity. So we're trying to write these approaching statements. Here, what's happening to the right end, left end? This is that cube root function. As x approaches infinity, the function is approaching positive infinity. As x approaches -infinity, the left end is going to -infinity. 12 is an exponential. So look at the right end and the left end. So the right end behavior is going to infinity, while the left end behavior is going to a number. And you count that 1, 2, it looks like it's -3. Number 13, the right and left end, can you see both ends are going to a number, not going to infinity. So we're going to say the right end, as x approaches infinity, while the right end's approaching and count up 1, 2, 3. And then the left end, we say as x approaches -infinity, what's happening to the left end? And you can see it's the same number, 3. Here, right end and left end, by this is a rational function, right? This is a parabola. As x approaches infinity, what's happening to the function? It's going to -infinity. As x approaches -infinity, the left end behavior, the function's also going to -infinity. Look at this. I'm not even sure what this is. Nice looking function though, isn't it? Something different. I'll have to think about what type. It's not a common parent function, but I can think of it. But right now it's continuous. So I know that if you look at the right and left end behavior, you can tell it's crossing over. It's actually going to get closer and closer to 0. So as x approaches infinity, the function is approaching 0 from the right, and as x approaches -infinity from the left, it's also approaching 0. So as we put in large numbers, it's getting closer and closer to 0. 16. Here we have a rational function again with an oblique. But 16, as x approaches infinity, the right end is going up to infinity. The left end behavior, you can tell, is going down to -infinity. Number 17, the right end and the left end. So the right end, that's as x approaches infinity, the function's going to a number. That number, as I count down, is -7. -infinity, the left end is going to positive infinity. One more about end behavior. So the right end and left end, you can see where it's going. So the right end is going to 0, while the left end is also going to 0. So both the right and left end are going to 0. All right, good job on continuity and end behavior.